Hello, Slush. So, two things. Should we start with the good news or the bad news? The good news. Okay, so the good news is that the ones that are waiting to see a presentation about building a petabyte pipeline will see something that is much cooler than that. That's the good stuff. So we will talk about machine learning and doing classification and source code abstraction with Vadim from Sourced. So hopefully you will enjoy it. I know this talk will be an excellent one.
Thank you. Let's see how awesome it would be. So I'm not sure if anybody of you were just 1 hour ago when Isa, our CIO, presented like ideas about machine learning, but this is more a technical presentation of what we are doing and our experiments with doing machine learning on source code. So you can scan this QR code and get this presentation on your web browser on your mobile device. I think it can be better for you. The plan is as follows. So first of all, I explain what we are and what we're trying to do. And then I'll pass over to extracting features from the source code. Present the neural network, deep neural network which we use to do that, and how Google's technologies help us to achieve that. Present the results and give some slides about other works which we try to do. So let's start. Basically, Sourced is a recruiting company. What we do is that we match job offers for developers with developers which we take from GitHub. And this is quite different from what other recruiting companies do because we are not matching CVs. We only take the source code. So it's not what we're using something which developer himself or herself writes, but rather like analyze the result of their work and find perfect matches with the job offerings. And we believe that we would be much better at what we do if we have a way to cluster developers. Well, it is kind of hard for several reasons. For example, if you are doing machine learning, for example, predicting sales or classifying images, you have a lot of research work, you have a lot of materials, a lot of samples, but nobody actually trying to look at a developer as a machine learning subject and kind of extract features from developer, from his source code, and use it. I believe that we are like the first who tried to do that. There are several sources of information which you can use if you want to cluster a developer. First of all, it's social networks. I mean, not only what we have in LinkedIn, but other social graph, other sources, analyzing his blogs, what he writes in forums. This is a good source, but it's complementary. It's not the major one. You can use machine learning based on version control. You can analyze commit messages. You can do topic modeling on commit messages, even predict how a project evolves and either it will be abandoned or not. This is also a good source of information, but again, not the major one. And finally, developers, of course, write source code, and we should analyze the source code. When I say that, we can focus on understanding algorithms. So basically, build some machine learning pipeline which tries to understand what is really happening. For example, you can code some quick search in Python, and your machine learning actually understands that this is quick sort and matches this implementation with other quicksort implementations. This is harder though somewhat achievable, I think, and I'm perfectly sure that either we or other company will succeed with doing deep learning on algorithmic source code stuff within the next 5 years. Uh, we can use dependency graph. Um, I mean, when you start a project nowadays, you're not likely to start it from scratch. You're likely to use some libraries, some pre-existing work, and these libraries also have some dependencies inside, and you end up with some tree of dependency, and it can try. It can help you to uh, classify and cluster source code and projects. And the last source is style. Source code style can correlate with how good you can program, because usually if you put clever names to your variables, if you have short functions, if you have good comments in good places and everything, you're like consistent throughout your code base, most likely you know how to code well, and you are better than a person who is fuzzy in the source code style. Let's check how we can analyze source code, particularly source code style, using machine learning techniques. On a toy task, let's take a binary classification problem with two classes. So basically what we try to do is to take two random projects, take like random 50 lines from every project, and classify whether these 50 random lines belong to project 1 or project 2. To do that, we have to find a way to extract features. And we have to take into account several aspects. For example, you should ignore some garbage, such as text files, markdown files, and everything which is not very much related to the source code. You should ignore auto-generated files, rendering in Golang, so on and so forth. You should support a lot of languages, because there are some attempts, prior attempts before we started doing what we do, and these attempts usually focus on just a single language, either Java or C or whatever, and our requirement is that we should analyze all the 400 languages out there on GitHub without any much labor-intensive work. The last point is that we should be as descriptive in our source code features as possible. It means that, for example, you could take only length of each source code line, or I don't know, count the number of every letters, while it can impose some good feature source. The features are prosodic and they don't mean as much. The first two issues are successfully solved for us by GitHub Linguist project. Basically, GitHub uses it to draw these nice language bars. So for example, your project contains 50% of JavaScript, 30% of Go, 20% of C. GitHub uses this project. It's open source. It's written in Ruby, so it is very slow. And if you want to analyze 18 million, it's going to take a lot of time. That's why we had to implement our own source code classification tool written in Go. The third and the fourth problem are solved for us by Pigments. It's a library written in Python which does source code highlighting. It's more or less what Sublime editor shows or recent JetBrains IDEs show. Every token is highlighted with an appropriate color, and it's easier to code in this way. So we use this. So we get tokens, a stream of tokens for more than 400 languages, and continue with them. This is just simple example, which is what is a source code highlight, and internally it is this 15 token types: token command, token text, token keyword. We can turn this token stream into features ready to analyze with a neural network using a one against all approach. So we just put zeros on every token type which is non-existent in the current value, and one on the place where the actual token exists. Well, it's not the best way of turning token stream into features, but most straightforward, and currently we are stick with it. This is our processing pipeline. So we split stream into lines, and we have to put some maximum line length. Otherwise, we will end up with arbitrary inputs for a neural network. We should have a fixed input. We merge indentations. Then some tokens are somewhat more complex than just one dimension. It gives us about 200 dimensions per token, and this is like multiplied by 40, apparently 8,000 features per line. So we can count how many features we have for a typical project with 1 million lines. We will get a lot of features. Thankfully, most of them are zeros, so we have very sparse input, just like a natural language processing problems. Talking about natural language, you may notice that my feature extraction scheme doesn't extract names. There's just no place for storing names, and this is a very valuable information in the source code. There are several ways of dealing with it. We checked two. The first is apply LSTM recursive neural network to do sequence modeling, and it gives you like very smart code suggestions. And by the way, Microsoft guys just have recently issued an article about even more smart way of doing sequence modeling. The second is topic modeling. Basically, you treat every project as a text document, extract names, and then subsequently extract topics occurring, in our case, in GitHub. Well, there are articles about that, so you can read it. So this is all about bag-of-words modeling, and our neural network doesn't work with bag-of-words. This is an example how a deep neural network sees the token stream. It's like source code highlight, but it's kind of squared. Every line is source code line. Every color corresponds to specific token type. In reality, it's more complex than that, but it should give you some idea. We are using 7-layer neural network. The architecture is, well, it resembles what, for example, MNIST dataset is analyzed with just basically TensorFlow, typical TensorFlow sample code. We just extended it and tuned the parameters. 4 layers are convolutional, 3 are fully connected. It is easy to just list all these characteristics of the neural network because TensorFlow has a very good formalized way of implementing deep neural network algorithms. So I just take parameters from code and list it there, so it's good. Our processing pipeline continues. So we merge all project files together, and our batch size is 50 abstracts, each with 50 lines of tokens. We should definitely try random shuffling, because without random shuffling, our neural network doesn't converge at all. Then we truncate projects so that we get the same number of source code abstracts for every project, Otherwise, our neural network will be biased. Our dataset is biased. This is our implementation of the neural network. We are using Python 3 and TensorFlow and train everything on NVIDIA GPUs. And this is runnable on CloudML, but most of our runs were just locally. We process projects with Dataproc, which is basically a managed Spark. This is really cool because Dataproc solves a lot of typical Spark setup problems for you, and you just can focus on doing stuff related with machine learning apart from debugging your Spark cluster. If you had to debug a 100-node Spark cluster, you should understand the pain. And we store the database of features in cloud storage. We have 18 million projects, and it gives us about several terabytes of extracted features, and cloud storage is really good for that. Just read-only storage. This is the result of analysis, and if you take projects written in the same language, the accuracy tends to be somewhat smaller, reasonably, because if you compare projects written in different languages, of course, it's very easy for a neural network to infer which language is the source code, so not surprisingly. Anyway, if you take Java projects, which are quite different, for example, Goava and Hibernate, you get 96% of the accuracy. But if you take Python projects, more or less similar Django Twisted, they're all web engines, you get about 84% accuracy. Apparently, if you just throw a coin, you will get 50% accuracy, so it's much above the baseline. I can draw a conclusion that the neural network sees the source code in a way that more or less a human being sees it. So it tries to extract first some lower level patterns in the style, then higher level patterns in the style, and end up with some internal similarity within the project. If you compare to projects which are very alternating inside, you are most likely to achieve worse accuracy. And this is just a simple example. So how like a human sees a Python source code. So yeah, he tries to think about, so he sees a keyword while, and he understands this is a cycle. Then he goes on and sees return. So he understands this, it's likely it's a function. He goes up and sees that this is def. Okay, so this is really a function. And yeah, he sees a long gap, so class method and everything. And we believe that a neural network actually extracts the same. Unfortunately, it's not very easy to get much introspection into the network because if you have a typical image classification or recognition task, you can just draw your kernels and get these nice pictures. Everybody understands that everything is good just looking at the images. When you see the source code, it's kind of trickier because, well, most of the convolution layers are just one dimension, so it's no sense in visualizing them. It's an open problem for us how to get this introspection, and I think there will be need some more research. Let's pass over to the other work. We clustered GitHub users using language vectors. So basically, you take every GitHub user, measure the number of bytes he wrote in each language, and here you go with features. You just cluster them with a reasonably big number of clusters, basically lowering the dimension. Then you run some stuff like TSNE or some more advanced ways to visualize your clusters and end up with this picture. So blue lines are developers which we have not contacted yet, and red lines developers which we contacted, Yellow dots are developers who refuse to be contacted. Besides, you may have heard about the recent article published on Medium by some Google guy about applying big table dataset, big table GitHub dataset to measure what is more widespread indentation with tabs or indentation with spaces. We believe that while the work is good, it can be much improved, and we kind of reproduced the results, but the results appear to be different. In our case, for example, spaces are most commonly used like everywhere, except some crazy languages like PostScript, ActionScript, and others. So you can go to the link and just look at this picture in detail because it's an interactive visualization. We did topic modeling of GitHub. We extracted 200 topics, and eventually we appeared very funny topics like GitHub repositories devoted to pizzas, GitHub repositories written in Spanish language, in Italian language, in German language, and it appears that PHP repositories written by non-native English speakers differ from PHP repositories written by English native speakers for some reason, but well, topic modeling confirms that. And a lot of other funny stuff. We extracted also a complete list of technologies, of web frameworks, and everything. There is an article, you can just view it. There is a Docker image, you can try it and analyze any repository you want. Talking about source code abstract classification, about smart code completion. This is what we achieved with LSTMs. So we just type several letters and get some kind of smart completion. Of course, it doesn't make much sense because, well, it's syntactically correct, but sometimes it doesn't help you at all. And I think Microsoft article solves this problem with making second layer which makes sense with naming. So let's see if we can implement it. All our data sets are open. You can download them on Data World. It's like GitHub, but for data scientists. So you can fork a data set, you can publish your data sets, whatever. We have two data sets. The first is GitHub repositories, all 18 million. And the second data set is duplicate repositories. So apparently 1.5 million GitHub repositories are duplicates. They're replicating others, but not marked as forks. This is it. Thank you. Any questions? Yep. Well, let me take it. So our current approach is applying magnet laws from Facebook. Okay, so the question was how we are doing our embedding with deep neural networks, right? So either we're using a deep neural network for embedding or just k-means, right? So our approach is hybrid. We apply k-means in some cases when we want to lower the dimensionality, or we apply Facebook PCA for the same reason, or topic modeling for the same reason. Our current way of doing embedding on developers is using GitHub projects as labels. So initially, we cluster GitHub repositories, get like 10,000 groups, and every developer contributes to some group, you know. Each developer is an image, and each GitHub group is a label, you know. Then we apply all the machinery from ImageNet and whatever, and we apply magnet laws to do nice embeddings, and we get some results. Yeah. What's even funnier is that it's very hard to cluster GitHub repositories because there are many criteria of actually doing this clustering. You can cluster them by naming, you can cluster them by number of developers, by language vectors, by commit prosodic features, whatever. And we end up with doing like several, like 10 different clustering schemes and getting like 10 different labels for the same developer. Okay, thank you.